There is something pulling our galaxy, not metaphorically, not in some poetic sense of cosmic destiny or gravitational destiny, literally, physically, measurably pulling it, pulling the Milky Way, and the Andromeda Galaxy, and the dozens of smaller galaxies that make up our local group, and the thousands of galaxies in the Virgo supercluster, and an enormous fraction of everything within several 100 million light-years of us, all of it flowing, streaming, falling in the same direction, at speeds that dwarf anything else we measure in the universe. Something is out there, something massive beyond ordinary description, something whose gravitational influence extends across hundreds of millions of light-years of space, and whose true nature was one of the great hidden puzzles of 20th century cosmology. It was named, with appropriate drama, the Great Attractor. And the most unsettling thing about it is this: we cannot see it. Not because it doesn't emit light, not because it's obscured by dust, but because it sits almost exactly in the direction of the galactic plane, behind billions of stars and thousands of light-years of interstellar gas and dust that block essentially all optical and infrared wavelengths. The Great Attractor lies in what astronomers call the zone of avoidance, a band across the sky where the density of intervening material in our own galaxy makes observations at most wavelengths essentially impossible. We discovered it by its gravity before we could see it, and what we have gradually been able to piece together about its nature, using radio waves, X-rays, and the peculiar motions of galaxies as a kind of cosmic seismograph, is more complex and more extraordinary than the original discovery suggested. The story of the Great Attractor begins in the 1970s, with an attempt to measure something that had never been measured before: the absolute motion of our galaxy through space. The universe is expanding. Every galaxy is moving away from every other galaxy, on average, because space itself is expanding between them. But this expansion is not perfectly smooth. Galaxies don't just participate in the cosmic expansion, they also have what astronomers call peculiar velocities, motions that are additional to the expansion, caused by the gravitational influence of nearby concentrations of mass. A galaxy near a massive cluster, for example, will be moving toward that cluster at a few hundred to a few thousand kilometers per second, on top of whatever velocity the cosmic expansion gives it. In the late 1970s, a group of astronomers studying the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky, noticed something unexpected. The microwave background wasn't perfectly uniform in temperature. There was a pattern in the temperature variation that looked like a dipole, one side of the sky very slightly warmer, the opposite side very slightly cooler, in a smooth gradient that corresponded to a specific direction. This kind of temperature variation is what you'd expect if the Earth and the entire solar system were moving through the cosmic microwave background at a significant velocity. The side in the direction of motion would appear slightly warmer due to Doppler blue shift. The side we were moving away from would appear slightly cooler due to Doppler redshift. The velocity suggested by this dipole pattern was remarkable. Our solar system appears to be moving at approximately 627 kilometers per second relative to the frame of the cosmic microwave background. 627 kilometers per second. To put this in perspective, the Earth orbits the Sun at about 30 kilometers per second. The Sun orbits the center of the Milky Way at about 220 kilometers per second, but relative to the cosmic background, the most fundamental reference frame the universe provides, we are screaming through space at over 600 kilometers per second. Part of this velocity is due to the Milky Way's motion within our local group of galaxies. Part of it is due to the local group's motion toward the Virgo cluster, the nearest large galaxy cluster. But when astronomers subtracted all the known contributions and looked at what was left over, they found a residual motion that pointed in a specific direction and couldn't be explained by any known nearby structure. Something massive was pulling everything in that direction, something that, at the time, lay in the zone of avoidance and couldn't be directly observed. That something was what they would come to call the Great Attractor. The initial estimates of the Great Attractor were staggering. The observed motions of thousands of galaxies across hundreds of millions of light-years could only be explained by something with a mass of roughly 10 to the power of 16 solar masses, 10,000 trillion times the mass of our Sun. Something occupying a region of space roughly 250 million light-years across, centered in the direction of the constellation Centaurus, at a distance of approximately 150 to 250 million light-years from Earth. These numbers were, to put it mildly, not easy to account for with known structures. Astronomers began looking for what could produce such a gravitational influence, and what they gradually found, as observational techniques improved and the zone of avoidance became partially penetrable using radio waves and X-rays that can pass through intervening material, was a picture considerably more complex than a single massive attractor. The first major revelation came when X-ray observations revealed a large galaxy cluster in the direction of the Great Attractor, the Norma Cluster, formerly catalogued as Abell 3627, sitting at a distance of about 220 million light-years. The Norma Cluster is one of the most massive galaxy clusters in the observable universe, a dense concentration of thousands of galaxies, hot intergalactic gas, and dark matter that contributes significantly to the gravitational pull felt across the surrounding region. But the Norma Cluster alone wasn't enough to explain the full extent of the Great Attractor's influence. Further observations revealed that the Norma Cluster is itself part of a larger structure, an enormous supercluster of galaxies called the Norma Supercluster, also known as the Great Attractor region, which extends across hundreds of millions of light-years and contains several massive galaxy clusters, in addition to Norma. This supercluster, taken as a whole, better accounts for the observed peculiar velocities, but it still doesn't fully explain the motions of galaxies across the entire region that appears to be streaming toward the Great Attractor direction. The reason, discovered in the following decades, is that the Great Attractor is not the largest structure in the game. In 2014, a team of astronomers led by R. Brent Tully published a paper that fundamentally changed how we understand our cosmic neighborhood. Using a new technique for mapping the peculiar velocity field of thousands of galaxies, identifying the boundaries of galaxy watersheds, the regions where galaxies stream toward the same gravitational basin rather than away from it, they defined for the first time the full extent of the supercluster that contains our galaxy. They called it Laniakea. The name means immense heaven in Hawaiian, a name that turns out to be entirely appropriate. Laniakea contains approximately 100,000 galaxies. It spans roughly 520 million light-years in its longest dimension. Its total mass is estimated at about 100 million billion times the mass of the Sun, roughly 10 to the power of 17 solar masses. The Milky Way, the Andromeda Galaxy, the Virgo Cluster, the Norma Cluster, and all the structures previously identified as components of the Great Attractor are all parts of Laniakea. And within Laniakea, all the constituent galaxies, all 100,000 of them, including ours, are flowing toward a common center. That center lies in the direction we previously called the Great Attractor, specifically toward the Norma Cluster and the broader Norma Supercluster region that marks the gravitational heart of Laniakea. We don't live near the center of Laniakea. We live in a relatively sparse region near its outer edge, one of the tentacles of the supercluster's structure, far from the densely populated central regions. And we are falling, slowly, on human timescales, but inexorably on cosmic ones, toward the center of this structure, along with everything else in our cosmic neighborhood. The Great Attractor, it turned out, is the gravitational core of our own supercluster. We had been mystified by it not because it was alien or exotic, but because the zone of avoidance was hiding the densest part of our own cosmic home. But here is where the story takes another turn, because even Laniakea is not the end of the hierarchy. The peculiar velocities of galaxies in the Laniakea region point toward the Great Attractor, yes, but they also show a residual component, a net motion that persists even after accounting for the gravitational influence of Laniakea itself. There is something even larger and more massive pulling on Laniakea. That something is a structure called the Shapley Supercluster, also known as the Shapley Concentration. It sits at a distance of approximately 650 million light-years in the same general direction as the Great Attractor, and it is the most massive known concentration of galaxies in the observable universe. The Shapley Concentration contains dozens of galaxy clusters, thousands of individual galaxies, and has a total mass several times that of Laniakea. It represents, as far as we can currently measure, the largest coherent gravitational structure within our cosmological neighborhood. And Laniakea is falling toward it. Not collapsing into it. The distances and timescales involved mean that the motion is gradual, and the accelerating expansion of the universe means that ultimately, Laniakea will never actually reach Shapley. The expansion of space will eventually overcome the gravitational pull, and the distance between Laniakea and the Shapley concentration will begin to grow again, as it does between most galaxy clusters and superclusters on large scales. But right now, in this moment of cosmic history, the net motion of everything in our local universe, including the Milky Way, including our solar system, including the planet you're sitting on, is a complex superposition of flows, toward the center of Laniakea, toward the Shapley concentration beyond it, and simultaneously away from other large-scale underdense regions that repel as effectively as massive clusters attract. We are caught in a web of cosmic currents, some pulling, some pushing, the net result of which carries us through space at hundreds of kilometers per second in directions that are only now becoming clear as our maps of the universe's large-scale structure improve. There's a practical question worth addressing at this point. If our galaxy is falling toward the Great Attractor, and the Great Attractor is falling toward the Shapley concentration, what actually happens? Will the Milky Way eventually arrive at the Great Attractor? Will it be destroyed? Will anything change for the people or whatever beings might inhabit our galaxy billions of years from now? The answer is considerably less dramatic than the word falling might suggest. The Milky Way's motion toward the center of Laniakea is happening at roughly 600 kilometers per second. That sounds fast, and compared to everyday human experience, it is genuinely staggering. But the distance to the gravitational center of Laniakea is approximately 200 to 250 million light-years. At 600 kilometers per second, crossing that distance would take on the order of 100 billion years, roughly 7 times the current age of the universe. And this calculation ignores the crucial fact that the expansion of the universe is accelerating. At some point in the future, the cosmological expansion will drive the distant parts of Laniakea beyond our cosmic horizon, and the structure itself will gradually lose coherence as its outer regions are carried away by the accelerating expansion. The supercluster is a feature of the present epoch of cosmic history, not a permanent structure. In the far future, as the expansion continues to dominate over gravity at ever larger scales, the concept of superclusters as coherent, gravitationally bound entities will become increasingly meaningless. So the Milky Way will not crash into the heart of the Great Attractor. It will drift in that direction, slowly, for timescales that vastly exceed the current age of the universe, while the universe's expansion gradually unravels the large-scale structure around us. On any timescale that matters for the future of life or civilization as we know it, the Great Attractor is a neighbor in the cosmic sense, close enough to exert measurable gravitational influence, but not close enough to pose any kind of direct threat on any humanly meaningful horizon. What the Great Attractor actually tells us, beyond the specific numbers and the specific structures involved, is something about the nature of the universe at its largest scales. We tend to think of galaxies as isolated islands in space, separated by vast voids, each one following its own path through an otherwise empty cosmos. The Great Attractor, and the structures associated with it, reveal that this picture is deeply incomplete. Galaxies are not isolated. They are participants in a vast web of gravitational influence that extends across hundreds of millions of light-years, connected by dark matter filaments, organized into clusters and supercluster complexes, all of them caught up in flows and counterflows that trace the largest structures in the observable universe. The peculiar velocity field, the pattern of departures from smooth expansion that the Great Attractor helped us first recognize, is a map of the underlying matter distribution in the universe. It tells us where the mass is, including the dark matter that doesn't show up in any direct observation. In regions of high mass concentration, galaxies flow inward. In regions of low mass, galaxies flow outward, driven by the relative underdensity around them. The Great Attractor marked the beginning of our ability to read this map. It also humbled us. For decades, astronomers had assumed that the peculiar velocities of nearby galaxies were small, that the universe, on the larger scales, was smooth enough that individual regions didn't move significantly relative to the average expansion. The Great Attractor showed that this was wrong. The universe, even on scales of hundreds of millions of light-years, has significant structure, significant mass concentrations, and significant departures from uniformity. The large-scale structure is not a subtle perturbation on an otherwise smooth background. It is a genuine, dramatic feature of the universe's architecture. There is something genuinely vertiginous about thinking through all of this carefully. The planet you're on is orbiting the Sun at 30 kilometers per second. The Sun is orbiting the center of the Milky Way at 220 kilometers per second. The Milky Way is moving toward Andromeda within the local group at around 110 kilometers per second. The local group is falling toward the Virgo cluster at around 250 kilometers per second. And the whole local supercluster, Laniakea, is streaming toward the Shapley concentration at several hundred kilometers per second more. All of these motions are happening simultaneously, in different directions, adding and subtracting to produce the net motion of our solar system relative to the cosmic microwave background of 627 kilometers per second. We are not sitting still. We are not moving at a human speed. We are hurtling through space at velocities that dwarf everything our civilization has ever built or imagined building, in multiple directions simultaneously, caught in a flow of matter that traces the largest structures of the cosmos. And the thing that initiated our understanding of all of this, the thing that first revealed that there was a pattern to the motions, that there was something massive and hidden pulling on everything in our region of the universe, was an anomaly in the temperature of a faint microwave glow that fills the sky, noticed by careful astronomers in the late 1970s. The universe told us it was moving. We listened. And the answer has been one of the most profound revisions to our picture of cosmic structure that modern astronomy has ever produced. The Great Attractor is not a monster at the edge of the known universe. It is our home, the gravitational heart of the supercluster we live in. And we have been falling toward it for as long as our galaxy has existed, and will continue falling toward it for as long as the universe remains in anything like its present configuration. We are not at the center of the universe. We are not at the edge of the universe. We are somewhere in a tentacle of a supercluster, drifting in the gravitational current of structures so vast they can only be seen by measuring the motions of thousands of galaxies across hundreds of millions of light years. That is where we are, and the Great Attractor is the reason we know it.